He loves chemistry 'cause it's fun. If that makes you crazy, then he's the one to teach you chemistry 'cause it's fun. He's chemistry coach. He's chemistry coach.
And one, and two, and three, and four. Come on, you can do it. Yes, Sisyphus, you finally got that thing over the edge, and it was all thanks to me. I just chopped the top of that mountain right off, and you finally got that rock over. Woohoo! Just lowered that activation energy, and it's all thanks to me. You owe me drinks later. But we ain't going to the bar. This is the COVID era. COVID-19 time. Just ship it to me, all right? Welcome to Chem Coach. I'm Coach Powers. And once again, we're here to learn some new stuff about chemistry. My goals are for you to have fun learning chemistry. I want you to enjoy the beauty and the wonder of chemistry. And hopefully, you'll get to understand this subject a little bit better from having participated in watching me in this crazy time. Well, today's lesson is on the activated complex, activation energy, and for a bonus, we're going to do some energy diagrams. So, for me, activation energy in the activated complex is like this crazy ball. Check it out. So, I don't know who invented this ball. It's one of the coolest things ever. It's called a switch pitch. The guy was a genius, crazy. The girl was a genius, crazy. I don't know. But this is a perfect illustration for what an activated complex is like. There's going to be a moment in time when I throw this. Oh, sorry, that was supposed to be slow-mo. Guess I don't have slow-mo. But you're going to notice that it kind of moves and it has this, whoa, it's magical. It has this moment where it kind of transforms and changes in the air, and it just changes from orange to green. Oh, there we go. But you got to get just enough of a throw on it. Let's see. Yeah. Oh, what was that? Oh, there we go. So, there we go. So, it's a really cool sphere. It basically has two ways to organize, and at one point in time, it exists like this. So we're going to talk today about the activated complex. And when we do, I want you to think about this being the activated complex, okay? And the activation energy is the amount of energy that I have to put into it to make that thing actually transform from orange to green. If you do little bits, it doesn't go, okay? It tries, it gets close, but it doesn't quite get there. Like Sisyphus trying to push that rock up the mountain over and over again, and it just falls back down, right? We'll talk about platinum later, probably in tomorrow's lecture. This is a catalyst, and we're going to learn about how catalysts can reduce the activation energy, but that's in another lecture. So, let's see, what else? When we're done with this lesson, okay, we are going to be able to describe the activated complex, and we're going to be able to interpret and sketch energy diagrams. So you'd be able to describe the complex in terms of energy, stability, and the role in the reaction pathway. And if I give you an energy diagram, you're going to be able to calculate the delta H, remember that means enthalpy, and the activation energy, and determine the energy of the activated complex. And if I give you energy data for a reaction, you would be able to sketch an energy diagram, because that's what we all like to do, right? What I like about this lesson is playing with this funky ball and playing with graphs that look like roller coasters. So join in with me. We're going to have some fun as we do this here today. And if you stick with me to the end, you might get to hear me sing, which you probably don't want to do. do a little Beatles rendition, which I think you're going to understand how Sisyphus got up the hill and put the rock over the edge with a little help from his friend, me, Platinum. Platinum was in Greek legend, right? Maybe? All right, so let's get to today's lesson. So, when a reaction occurs, there's got to be a minimum amount of energy that you're going to need to get to the top of that hill and then to go over the other side of that hill, right? If you can get that minimum amount of energy to get up to the top, that's called your activation energy. And again, you'll see these hills in a second when we do our energy diagrams. Okay, that's the amount of energy that's necessary to convert the reactants into the products. Now, if you have enough activation energy, you get up to the top of that hill, right at the top of that hill for that instant, that very brief moment in time, you have this kind of interesting combination of a reactant molecule, product molecules, and you end up having something called the activated complex. Okay, one of our diagrams here will show you kind of like this combined molecule of both the before and the after. It's kind of like seeing into the future while looking at the past. But that's called the activated complex, okay? And again, this is just something that forms for a brief moment in time, and it's represented by the peak of that diagram. And remember our little illustration at the beginning, we had that activated complex was like, woo, magical moment, right in between the orangey and the greeny, right? That's the activated complex. Now, before I go on to the next concept and actually have you get quizzed a little bit on this, I stumbled across something interesting. One of the things I like about this particular lesson is it makes us kind of reflect on our personal activation energies. All right, so I was just looking at another site, and they brought up this quote by Osho, who's an Indian spiritualist, metaphysicist. Anyway, don't necessarily agree with everything that he's saying here, but it's pretty interesting. Look at the quote. Oh, it's backwards. Sorry. Guess you'll have to look at the screen. But the quote's kind of interesting. I'm not going to read it out loud, but I'm just going to basically summarize it for you. Two forms of energy. One where you're always trying to get to that goal, right? So you're going up the hill, and it does kind of seem like Sisyphus sometimes, because although the rock doesn't roll back down, we always seem, once we get right to the top, it's like, yeah, it's not enough, let's get to the next goal. We're always setting this new goal for ourselves. I don't think that's necessarily a bad thing at all, but it is an interesting perspective. Osho presents here, Osho, don't know how you pronounce his name, Osho. Osho. But he then says that second dimension of energy is this relaxation, unmotivated energy. So you have this motivated energy where you're always striving to get to a goal, and then he has this unmotivated energy where you're just like, oh, I found my inner peace. Right? Have you seen it? No. Got the reference? I hope. Anyway, it's kind of fun. The goal is here now. The goal is not somewhere else. In fact, there is no other fulfillment than that of this moment. Consider the lilies. When you are the goal, oh, yeah, interesting. And when the goal is not in the future, when there is nothing to be achieved, nothing to be achieved, okay. Rather, you are just celebrating it, then you have already achieved it. It is there. This is relaxation. Unmotivated energy. I've done it. I've fulfilled it all. I'm the criminal. Thank you. Anyway, kind of an interesting thought. What it makes me think of is going up this hill. That's the goal, right? That's the motivated energy. And once you get to the top of the hill, you hit that activated complex. Then you have this relaxation energy, this unmotivated energy. Now everything that you've worked for is now, it all just kind of goes along. So it's kind of like a chemical reaction. You have this energy that's produced because you've worked for it, right? And so that's why it doesn't quite fit into his philosophies, because you actually do have to work in a chemical reaction to get up to this point and then work your way down. But speaking of activation energy, have you thought about burning paper? because that's a perfect example of activation energy, right? So, why is this paper not immediately combusting in my presence? It doesn't have enough activation energy. Think about it. You've got to get a match, or maybe stick this thing into an oven, get a really, really high temperature. Maybe it'll start to burn up a little bit, right? So you have to get enough energy to get that reaction to proceed. That's going up the hill so that you can go down the hill. So that's a good example of activation energy. All right, so the activated complex. You're trying to answer these questions now. Not me, you. The activated complex is a high or low, or should we do it this way? High or low potential energy compound. Thinking. Activated complex way up there. Complex is way up there, therefore must be high. All right, good job. Next one, the activated complex is stable or unstable. Which is it? Let me think about this, Powers. I'm considering. Unstable. You're right. You're so right. It's not stable. It's just briefly there. It's an unstable compound. And then the next question, the activated complex is important because it is it intermediary compound or molecule, or is it a permanent compound or molecule? Well, you know this one. Because the activated complex does not exist for a very long time. Therefore, because it's brief instant in time, it must be intermediary. Powers, why'd you use such a weird long word? Why don't you just say temporary or something like that? I don't know. Intermediary is a cool word. All right, so good job. Now, energy diagrams. Let's look at these two energy diagrams. Over on the left, you can see kind of the build-up with the numbers and all that kind of stuff. On the right, you can see the molecules. Now, this is the same thing we looked at in yesterday's lecture. Remember, we showed the bromines coming in and the NO, and like the NOBRA, right? The NOBRA molecule. Well, that NOBRA molecule is coming together. If it's oriented right, collision theory, oriented right and has enough energy, then it's going to react. Well, right at the top of that peak there on that right side, you can see that those two bromines are starting to like, yeah, hey, come here, buddy. Hey, let's be partners. And they're going to go off together, right? And then no is going to know they're going to get out of there. So, but on the left, when you look at that diagram, you can see a couple things. One thing, I want you to notice that the reactance is higher by the time you finish than the products, right? And so because the reactance is higher than the products, that should tell you what kind of a reaction this is. Energy, more, less, start, end. Oh! That means I'm more stable by the time I finish up and I end up in my products. Therefore, I've released some energy. Therefore, my reaction is... Yes, that's right. Exothermic, very good. So you'll notice we have that E sub A. I told you we'd be talking about that in yesterday's lecture and in the previous lecture. And the activation energy is the energy all the way from the reactants to the top of that peak. Okay, that's your activation energy. And you'll notice in the box, activated complex right here. Okay? All right, so then the other little symbol that you see in a box has got that delta H, and so that's your overall enthalpy. Would that be a negative value or a positive value? Very good, Joe. Absolutely. What? Positive? Yes. Of course, it's positive. Because remember, negative is exothermic, and this is... Wait a second now, I tricked you. All right, so this is exothermic, right? It released energy, therefore it must be a negative value. You almost fell for it, didn't you? But you're too smart. Way too smart, aren't you? Too smart for me. I know. That's why I got a funny look at my clothes. All right, now you're going to try it. So let's look at this example here. We've got some hydrogen bromide being heated up to form this H2Br2. That is not a permanent molecule. That is a intermediary. Therefore, it is our activated complex. Thanks. And that's going to then make some hydrogen and some bromine gases, right? Is bromine a gas at this temperature? I don't know. Remember, bromine's the liquid at room temperature, but with the heat, I'm going for gas. All right, so first question, endothermic or exothermic, right? We start down here with our reactants and we end up here with our products. Therefore, we put energy into the system. Therefore, it is endothermic. Good job, buddy. All right, then number 2, we have to label. I'd like you to take a permanent marker and write on your screen. No, just kidding. But I will label for you the reactants, the products, the activated complex, and the delta H. So I'm going to let you think for a second. Reactants. Products. Okay. Activated complex. Got that. And delta H. Ooh. The difference between my reactants and my products. All right, you got it. Good job. And then number 3, calculate the values for activation energy in delta H. Oh, okay, I can read a graph. I start at 80. Activation energy goes up to like 245 maybe? And then I subtract those two and I'll get my activation energy, right? And then my delta H starts at 80, goes to 160, positive or negative value. Am I going to trick you again? Endothermic is positive. And then, how would a catalyst change the diagram? Remember, I'm the catalyst. Platinum, I chopped the top of the mountain off, remember? So Sisyphus all of a sudden was going over to the other side. So, catalyst, chop the top of the mountain off. Okay? That's what happens with a catalyst. Lowers the activation energy. All right. So, now let's see if we could draw an energy diagram using HI. I've got 2 hydrogen iodide, monoiodide, 2 hydrogen monoiodide, and it's going to create this intermediary, this activated complex, and then it's going to form my products, hydrogen gas and iodine. Is it a solid? Is it a gas? I'm going to guess solid here because the heat's on the right side. I don't know. I'm really not sure what that would be in this particular reaction. I've not actually done this reaction in real life. This is just virtual for me. Sorry. So anyway, okay. Okay, are you imagining the graph? Does the reactant start above and the products below? Or are the reactants below and the products above? I will let you think about it. Heat's on the right side of the reaction, right? It's a product. Therefore, this must be exothermic. Therefore, the products has got to be lower than the reactants, right? Got to give off some energy. All right, let's go. And I think that kind of summarizes what we have done for today. So, can we now describe the activated complex? Yeah, absolutely. Crazy ball thingy. Yeah. Can we interpret and sketch energy diagrams? Of course we can. We are brilliant. And if I were to give you an energy diagram, here's one energy diagram, then you would be able to calculate delta H and the activation energy, and you would be determining the energy of the activated complex. We just did that. Unless you were just lazy and you let me do it for you. Don't be lazy. And given energy data for a reaction, you have 933 kilojoules. Then could you sketch the energy diagram? If you started with 15 kilojoules and ended up with your products at 20 kilojoules, could you sketch that? Could you make a graph? Yeah, you could, because you're the boss. All right. Good time? Had fun learning chemistry with you, as always. And just remember to go back and rewatch if you're still confused, and make sure to leave any questions that you might have in the comment section. I'll try to get to those. And don't forget, like the video if you liked it, and subscribe, because then you can get these videos immediately, like right away, as soon as I publish them to the interweb. I like saying interweb. Makes me sound cool. This is Chem Coach Powers, signing off for the night. Thanks. All right, bonus content. Fun fact of the day. I felt pretty smart today. Went to the store, got myself some hand sanitizer. But wait a second. Coach Powers, there is not a single bit of hand sanitizer around in any store. I'm sure that I've been to them all. So you say. But with a little knowledge of chemistry, this is why you're taking this class, then you might know where to look. Guess what I found? Woo, smelled pretty good. I found some aftershave. Number one ingredient. Anyway, as I was saying until my iPad so rudely interrupted me by telling me I'd run out of memory, was that I found aftershave. Number one ingredient, denatured alcohol. And if it's the number one ingredient, second ingredient's water, I'm guessing we're getting pretty close to 50%, which is what they recommend. So, splash it on after I got out of the store. Felt clean and sanitized. Nobody else knew about the aftershave. There was plenty of aftershave in the aisles. Shh, don't go buy that. That's all my aftershave. No, really. I just bought one. Just go buy one. Don't hoard. Hoarding's bad. Fun fact. What would you think if I sang out of tune? Would you stand up and walk out on me? I sure would. Lend me your ears and I'll sing you a song, and I'll try not to sing out of key. I've already done that. Well, I get by with a little help from my friends, just like platinum. I get high with a little help from my friends. High up in the mountain, try with a little help from my friends. Try and do some chemistry problems, yeah. Would you miss the intro? I get by with a little help from my friends. Oh, I get high with a little help from my friends. High up on the mountain. I'm gonna try with a little help from my friends. Try and do some chemistry problems. Yeah, baby.